My name is Yumin Oh. The paper I am going to present is called Dynamic Trend Demand Estimation and Passenger Assignment. In recent years, public transport travel demand has been rapidly increasing as more and more people living in cities. For example, London has got a 70% increase in public transport opportunity over the last 20 years. Another example, Sydney train network has reached more than 370 million opportunity in 2019, more than 70% increase since 2013. Given this situation, understanding passenger flow in the train network is significant. It can improve situation awareness. When there are service disruptions, it can help to respond to the disruptions quickly. It also can help transport planning for the future development. The research problem needs to be solved in this work is to estimate the passenger flow in the train network. This problem can be divided into two sub-problems. One is to estimate the time-dependent OD matrix. With this OD matrix, we can know where the passenger from and where the passenger go, and when they travel. The second problem is passenger assignment, which is to assign passengers to specific trains so that we can know what paths the passengers travel from the origins to destination. We use three main data sources in this research, including network layout data, timetable data, and station opportunity data. Network layout data has the information about train stations and the connections between train stations and also the platforms in each station. The second data source is timetable, which include the information about departure time, arrival time, and stations. The last one is the station opportunity data, which is about the number of passengers tap on or tap off at every stations. There are a number of challenges in this research. The first one is the opportunity data we have is aggregated for every 15 minutes time interval. We don't know the exact time the passengers tap on or tap off at stations. The second is we don't know which tap on data and which tap off data belong to a same passenger. In other words, we cannot simply get the OD pairs from passenger data. The third challenge is that we don't know which train the passengers get on after they enter the stations. The fourth is caused by the in-station transfer. From a same origin to a same destination, there may be several transfer options available. Passengers could choose any one of them. We need to estimate which one they choose. This research needs to deal with the above four challenges. The method for estimating the time-dependent OD matrix is divided into two steps. The first step is to build the initial OD matrix based on opportunity data and train network data. In the first step, a path routing engine is used for finding the shortest path between two stations. After we got the initial OD matrix, the second step is to use timetable data to calibrate the initial OD matrix. In the second step, a trip planner engine is used. Here's the diagram showing how to build the initial OD matrix. The input is the opportunity data, which is aggregated for every 15 minutes. Firstly, we use the sampling techniques to get the tap-on data at 1 minute time interval frequency. And then, for each tap-on, we use a path routing engine to find the shortest path to other stations. After we got the path, then we run the departure time and arrival time to 15 minutes interval. And then we do the trip distribution by a granularity-like model to calculate the time-dependent OD matrix. The time-dependent means each OD matrix is for a 15 minutes time interval. For a whole day, 24 hours, there are 96 OD matrices. Finally, we check the error against the opportunity data in terms of type of count. If the error is less than a given threshold, then it stops. Otherwise, it will go back to the sampling step, and then do again until the stopping condition is satisfied. After we have the initial OD matrix, then we calibrate the OD matrix by timetable data. For each OD pair in the OD matrix, we use a tree planner to update the path in the first step. The update means we calculate the arrival time using timetable instead of using distance between train stations. We also consider the waiting time and transfer time. The other steps are similar to the steps in the initial OD matrix estimation. The last step of our methodology is passenger assignment. This diagram shows how we model the passenger status change in a station which has multiple platforms. In the diagram, the circle A means the status of arriving platform, and the circle D means the status of departure from a platform, and circle S means a station entry or exit. The red arrow means platform to station exit. The red dash arrow means transfer between platforms, and the black dash arrow means remaining in a train, and the blue arrow means station entry to platform. With this modeling, we can estimate the passenger flow in a stations by using these formulas. For example, we can calculate the number of passengers remaining in the same train and a platform, the number of passengers exit from a platform, the number of passengers transfer from a platform, the number of passengers enter to a platform, and number of passengers transferring to a platform, and the total number of passengers in a station. To verify our proposed methodology, we carry out a case study which focuses on Sydney train network. The Sydney train network has 175 train stations and 506 platforms. In this case study, we need to estimate 2.9 million time-dependent OD matrix pair. Here we report the OD matrix estimate by our method for 11 selected stations, which includes 3 major train stations in CBD, Central, Town Hall, and Vineyard, and 8 other interchange stations outside CBD. We use hidden map to present the OD matrix. So this is the OD matrix on AM in the morning peak hours, and this is the OD matrix on 12 p.m. and this is the OD matrix on 5 p.m. in the afternoon peak hours. So in each hidden map, the dark color means the larger number of passengers traveling. So this is the stations the passenger travel from, and this is the stations the passenger travel to. So we can see in this hidden map for the morning peak hours, and there are more people are traveling to the 3 CBD train stations, which shows the pattern that the people are traveling to CBD for work. On the other hand, in the afternoon peak hours, there's more people are traveling from the 3 CBD train stations, which shows the pattern that the people are off work and going home. Stack bar chart shows an example of passenger flow in Town Hall train station on AM, 12 p.m. and 5 p.m. respectively. In the bar chart, the green color means the passenger getting off the train and go to train station exit, and orange color means the passenger getting on the train from the train entry, and the red color means the passenger traveling from other platforms, and blue color means the passenger traveling to other platforms. So in this bar chart, we can see in the morning peak hours, there's a lot of people get off the train and go to the train exit. Also, we can see a lot of people transferring between platforms. The people are likely transferring from platform 5 and also are likely transferring to platform 3. But in the afternoon peak hours, you can see there's a lot of people entering the station and getting on the trains. And there's people are likely transferring from the platform 2 and are likely transferring to platform 4. In this work, we have developed a method to estimate time-dependent OD matrix, which consists of 2 steps. The first one is initial OD matrix generation, and the second is the OD matrix calibration. We also propose a method for passenger assignment, which can estimate the passenger flow and platform level of granularity. Finally, we apply our methodology on semi-trained work. The results prove our methodology. Thank you for your time.